Now that we've learned a little bit about the atmosphere, we've got to understand how the energy gets in the atmosphere. And this week, that's what our focus is going to be, the energy coming into the system and out of the atmosphere to maintain this a stable and a habitable planet. So with that, the energy coming in is electromagnetic radiation, the sun's rays. They are radio waves or different types of waves that, like radio waves, transmit through the air. They contain energy, these waves, and most of the waves that strike the earth are in the form of ultraviolet radiation. And a lot of that is, part of that is the visible spectrum. So we can see a lot of the radiation coming from the sun. So we got to learn a little bit about waves first. So a wave has a wavelength. It is just what it says. It's two cresting waves, and between the two crests is a trough, and the length between the two crests is a wavelength. So I always like to think of waves like I think of the ocean, I guess, and I have a wave hitting me where I'm kind of duck under it, then it goes down by my legs again, and then back up again to the higher. And the time it takes, or the distance it takes to go between those two waves that are hitting me, is the wavelength. Sometimes they're real close together and you just keep getting socked. And sometimes they're pretty far apart. The same happens with electromagnetic waves. The closer together they are, the higher the frequency is, and all electromagnetic radiation moves at the speed of light. So that means that the shorter wavelengths have more energy. So you have more waves passing you, bringing more energy to the bear. So one of the things that's interesting is that many things are a black body. It has a constant temperature that absorbs all radiation it receives and emits it back out into space at a different temperature, however, at a different wavelength. So a true black body is a perfect absorber and a perfect emitter. Guess what? The sun and the earth approximate black bodies. The sun is much, much hotter than Earth, therefore it has a whole lot more intense radiation that's setting out. And the Earth, while it is cooler, still has a lot of shorter wavelength radiation that it's sending out. And because the temperatures aren't changing between the two, guess what? It shows that the black body, the amount of radiation reaching the Earth and being absorbed, is fairly constant. It hasn't changed over the years so much. An interesting thing about radiation is that it is inversely proportional to the absolute temperature. It's Wendell's law. And so that the shorter the wavelength, the higher the temperature. That's all that is saying. And here it is. And you can see most of the wavelength from the sun is in ultraviolet or visible range. And when you get over to infrared, you're getting down more towards our temperatures of our Earth. So most of the sun's radiation is visible to ultraviolet. The Earth's radiation, on the other hand, is infrared. And that is important to know. Another interesting thing is that the temperature of the body to the fourth power is how much energy it's emitting. So compare the sun's temperature to Earth. The sun is a whole lot hotter than Earth. So T is going to be much, much greater with the sun. And then you're going to use it to the fourth power. So its amount of energy is phenomenally larger than the amount of energy coming off the Earth. So that's why the sun is our main energy source. Another thing, the further away from the sun, less energy is coming into you. So It's 1 over the radius squared that you're away from the sun. Being 1 for R is the same as Earth. So say you have something that is 2 times further away, it would be 2 squared, or 1/4. It would be 4 times further away, it'd be 1/16. So you can see, if you know the distance of an object from the sun, you can estimate the amount of radiation energy that is actually coming to that object. Here we get more complicated. Think about the sun. The sun is directly over your head, basically at the equator, or in that general range between the Tropic of Cancer and the Tropic of Capricorn at some point during the year. So it is like a flashlight shining directly down on you. Notice that when a flashlight is shining directly down, it doesn't cover a very big area necessarily, and it's a whole lot more intense. It's a lot brighter. Now, if that sun flashlight is at an angle, and guess what? We live north, well north, compared to where the equator is. So our sun is hitting at an angle when it's up here. So the sunlight is actually spread out, and any one individual point where we are does not receive as much energy as you would receive down by the equator. And by the time you get to the North Pole or the South Pole, it's a lot less. And there's actually something called a solar altitude. Solar altitude is just the angle that the sun is striking the Earth at. So if you're at 45 degrees north and it was coming up here on the equinox when the sun is at the equator, the solar altitude would be 45 degrees. And guess what? At the North Pole, solar altitude is 0 actually. It doesn't have any sun until after it gets past the equinox, when the sun has moved back into the northern hemisphere. It begins to get a little bit of sunshine. So with that, you can see Antarctica, almost no temperature change when the sun's not striking there. But places like Singapore, I don't have a lot of temperature change either, because the sun is fairly high in the side, fairly directly really hitting them. However, where we live, Brookport, Mass, New York, or wherever here, even Ohio, you can see it goes up and down dramatically throughout the year. Look at the sun in relative to the Earth's orbit. The Earth is tilted. So here it is at an equinox, and we're pointing right into the equator. That tilt is not pointing towards or away from the sun at that moment in time. Wintertime, the northern hemisphere is pointing away from the sun. The sun is actually a little bit closer to the Earth in the wintertime than it is in our summertime, but not enough to make a large difference. But you can see as this thing's rotating around, come back to March, almost directly, the sun can't see the tilt. And summertime, the sun sees the tilt as being towards it. So we get more radiation coming in the northern hemisphere. So there are several things that happen with solar radiation that comes in. It doesn't all hit the Earth and just stay here. Some of it's scattered through clouds. And here, for example, you can see, this is just an example. It goes in every different direction when the sun hits a cloud. Some of it comes down towards the Earth. Some of it comes at an angle, different angle. But all of that, and that scattering is actually what makes the sky blue. When it hits the atmosphere, some of that scattering is what causes me scattering, it's called, and it makes a blue sky. Reflection of radiation from the sun is another one. Think about it. You had a lot of snow in Ohio there for a while. Did you ever walk outside and have a bright sunny day during that time and it really seemed bright outside? That's the snow reflecting the sunlight back up into space. So that instead of the Earth getting to absorb that sunlight, it's getting reflected back out into the atmosphere away from you, thus keeping you colder. There are certain chemicals in the atmosphere that do absorb it, and one of those UV radiation is absorbed somewhat and broken down by the chemicals in the stratosphere. That's why having an ozone hole is not a good thing, because you want most of that UV radiation, really bad UV radiation, not to make it down to the Earth. It warms the upper stratosphere because of that. But if that came down here, we would all have very bad cancers. We'd be probably dying. And you can see here, solar altitude, again, the change, more reflection. And here, look at the snow. Really stands out, doesn't it, on the satellite image? You can see a little bit in the mountains of West Virginia, a little bit along the lake here, Lake Erie. And lakes are much darker. They're absorbing the sun. So that's a difference. The darkness absorbs this radiation. The lighter reflects it. So when you're looking at the Earth from above, you can actually see dark areas and light areas where the Earth is absorbing radiation and where the Earth is reflecting it. The actual amount of energy reflected by the Earth is 30%. The atmosphere absorbs 23%, and the Earth's surface actually absorbs 47%. So, and they're relative. They may change a little bit from day to day. And you can see that by the fact that the Earth's atmosphere is the hottest near the surface of the Earth and cools as you go up. And then we have the ozone breaking down here, protecting us from the UV radiation and making it hotter in the stratosphere. There is something called the greenhouse effect. And the greenhouse effect is necessary if we're going to stay alive on Earth. We need the temperature on Earth to be a little bit warmer than it would be just if we had pure no greenhouse effect. It would be colder than it is right now. However, too much greenhouse effect is not a good thing. If you ever heard about the atmosphere on Venus, they have a lot of clouds, and they have a tremendous greenhouse effect on Venus. And it keeps the temperatures at the surface of that planet upwards of 500-600 degrees Celsius. Our greenhouse effect isn't anywhere near as powerful as that. Of course, we're not as close to the sun either. But that planet would be a lot colder without its greenhouse effect. So what is the greenhouse effect? Well, it's infrared radiation, which is, again, we say the Earth is not as hot, so it transmits infrared radiation back out to space instead of the ultraviolet or more towards visible light that you would find from the sun. And that transmission of infrared radiation then is absorbed by certain types of gases. So the principal one of those gases is water vapor. It contributes the most. The second most is carbon dioxide, then ozone and methane. So if you increase those gases in the atmosphere, more of the radiation from the Earth is going to get absorbed by those gases and come back to Earth to continue to heat it up. So, for example, if you live on the Gulf Coast versus the Southwest U.S., pretty much the same latitude, same amount of radiation, but the Gulf Coast has a lot of moisture with it. The greenhouse gases are higher, so it tends to be warmer, especially at night, than the Southwest, where it cools off so much at night. Another thing is the calendar effect. Basically, or the Keeling curve, they started tracking carbon dioxide back in 1957 out at Mauna Loa. It has been going up steadily ever since, and going up at increasing rates. But it doesn't account for everything in global warming that's going on. The reason being, it only takes in carbon dioxide. We already talked about water vapor being a part of it. methane, which isn't even a big amount in the atmosphere, but is extremely effective as a greenhouse gas because a small amount can have huge impacts. So all of this means that the Keeling curve just, doesn't see the whole picture. It sees some of the picture. So with that, I just wanted to talk a little bit on what you can actually see in the atmosphere. Here is a satellite picture. It's a visible satellite, but it changes to infrared as the sun comes by. Notice the line right here. That's sunset. Notice how the sun is setting later in the south than it is further north. Remember the curve. Remember that the sun is closer to the south, just very close to the equator, just a little bit south of it now. So the further north you are, there's a tilt to how that sun is hitting. So you actually get a shorter day further north and a longer day down south. And there are a whole bunch of different curves that a satellite can look at. So if we were to look at, for example, we have visible, we have infrared that actually shows vegetation, we have infrared that shows cirrus. These are all IR radiations that show different levels of the atmosphere and different things we're looking at. We can look at clean infrared, which is right straight from the ground or any surface or cloud, for example. And if I bring that up here, we're going to see colder cloud tops here, much colder runs up here, warmer. And you're actually seeing the surface temperature right here. When we had that extreme cold snap a while ago, you would actually have seen extreme cold all the way up into here. So you can actually see it, the curve that is used on satellite images. So there's a lot of ability knowing which type of infrared radiation you want to look at to be able to analyze different layers of the atmosphere or different aspects of it, like water vapor. So that's how all this radiation relates. Now, this gives you your energy. The next section we're going to talk about is temperature.